Hello, my name is Rafael Padilla Perez, and today I'll be walking you through my project. So let's begin first with our header file and our different classes. So first I set some macros for the render width and render height, so that we don't use magic numbers everywhere. I also created a ray class, so this has all the T, the classic parameters, then also a scene object class, which has a scene object constructor, of course, a draw, and an intersect function, which are inherited by all types of objects, in this case spheres and planes. It also has a t value, so that we can order objects toward the camera. It also has a point in space, and a diffuse and specular color, which the specular color will be used in the next project. We also have a sphere class, which has a point, a radius, a color, diffuse, specular, of course inherited from its parent, and then a constructor here, of course. And it has two functions, draw and intersect, inherited. Same thing for the plane, pretty similar. And I also created a custom view plane class. What I did for the plane is to have a draw and update function. So draw draws the update this plane in 3D space. Update just makes it set to the current camera's position and perspective. I also have a plane to world function that, given a UV coordinate, returns points in that plane, no matter its orientation or position in space, and a primitive, which is used to draw that plane. I also have a normal vector for the plane, a point for the plane, a width and a height, which in this case are just I'll render width and height divided by 100 to make it a reasonable size. Then we have a Raytracer where I have just a render cam. I'm only using one camera on this project and a view plane. So the render cam is what we use to move around the scene and explore around it, and the view plane is what we use to actually render, and I will show you in a second what that looks like. Also out, which is the output image, a vector of scene objects, which are the objects in the scene, or circles or planes. Then a couple of variables that are used just for as flags, a render function, ray trace function, and progressive render function, which I'm dying to show. Then here we have in our Face app just another couple of flag variables. We also have our GUI variables for this little GUI menu right here. And let me show you the code. So first of all, here we have a couple of global variables or parameters. We have our ray tracer, so a ray tracer class. Oh, I think I forgot to show that actually. Ray plane, view plane, ray tracer. So sorry, forgot about that. Yeah, I already mentioned it. So a render camera, a view plane, the image. So everything is within the ray tracer class, which is actually inheriting from the base application class, so that we can access Open Frameworks features, of course. So I just wanted to separate what is Open Frameworks here and what is the ray tracer here to have a little bit more of a modular code. Okay, so now we can go into the Open Frameworks region. Let me collapse this region over here. So in our setup, we just set the background color to black, of course. Then we set up our GUI. Then we set up the preview camera just to a random position. And then we set our scene objects, which are the plane and our three spheres that you can see right here. Then we also have previous position that is used to essentially, oh, I think it's not used. Yeah, ignore that for now. Our update function, which all it does is check if we're interacting with the camera so that we can run our functions. So, oh yeah, we do use previous position. So this is just a temporary variable to check if the camera's position has changed. If the camera's position has changed, then we are essentially gimbaling or interacting with the camera. And that is used to know when to remove the image that has been rendered and when to stop the progressive rendering. Oh, I gimbaled, so I hate this function of Open Frameworks. Let me open that again in the meantime. Okay, then we have progressively rendering. So using those flag variables, we check whenever we are not moving the camera, and then the progressive rendering takes place. So what we do is set color, start showing the image, and use this sampling method, which has the samples that I showed on top. So this is the current sample number, and this is the number of samples we want. In this case, I just put 50 to do a little demo. There's also a little save message for whenever we save an image. And then we have our draw function. So I enable the depth test and of course disable it at the end so we can see how the blue sphere is in front of the others because of the depth test. Then we also start working with the render camera as usual. we also have this function to show or hide a grid. So let me actually demo that. So we can show or hide a 3D grid with our X, Y, and Z planes, which is a really nice feature by Open Frameworks. And then we also draw these spheres. This is the preview of the spheres, not the ray traced version of the spheres. We also draw this render plane, which is the one I was talking about. So I can turn on show last view plane right here. And this is the render plane that we will be rendering from every single time. Then the camera. And then here I have displaying the images in the viewport. So all this does is set the color and draw the image. And it has this little clause that is for progressively rendering. So this is only used whenever we have the progressive rendering feature turned on. We also have our GUI to get a drawing. And now we can go into the ray tracing portion of this assignment. So first we have two main functions, which are render and progressive render. So render just renders a snapshot of the scene without any progressive rendering, just goes through each pixel and goes to them and renders that. Pretty simple. It also gets a time when it begins and when it ends. So just a little delta, t0, so current time minus that delta is going to give us the total time it took to run this whole function, this whole code. Then we also allocate space for an image, and we also start rendering the image. We go through each pixel, U, then each pixel V, which are vertical, and set the color depending on the ray trace function. Then we update the image, set this flag that has been rendered, and print that we're complete. Then we do the same thing in progressive rendering, but we use that sample variable that I showed earlier with this little modulus function. So all this does is it samples not random, but distributed points on the screen, and it essentially runs in a couple of iterations. And you can see we only finish rendering after we have reached 0. Then we have a ray trace function, which is pretty simple as well. So all we do is normalize the direction of this view plane minus the origin of the camera. Then we also build a ray from that. We also have a low variable, which is used for sorting objects, and nearest is a null pointer. Then for each object in the scene, if that object intersects with the ray, if that object is less than low, which is this variable, we update that variable and set that object as the nearest. So all this is doing is finding what do we intersect with and which one is the closest. So if there is a closest object, meaning if we intersected with anything at all that is the closest, we just return this diffuse color in this case. And I don't know why I have two semicolons there. Otherwise, we just return black, which is the background color. I should probably make this a macro global variable at some point. Then we also have a viewplane draw function, pretty simple. Just draw this viewplane on the color green with its parameters, position, width, and height, and resolution. Then we also have the update function. All this does is set and align the viewplane with the camera. So whenever we run this function, this just sets this green plane, the viewplane, to wherever the camera is currently facing. Then we also have the, actually, let me demo what a render looks like. So let me do a render image right here. And you can see we have rendered. And if I move around, you can see the plane has been updated to that position right after the render. So let me render again. So we can, I gimbaled again. Gimbaling is currently not supported, unfortunately. Not gimbaling, rolling. I think that's roll. Yeah, I think that's roll. So we can render from any angle. And yeah, as I was mentioning, you can see where the last plane was, so like that. So to have like a perspective on where you did it from. Then we also have this plane to world function. All it does is given UV coordinates, it just normalizes them from -0.5 to 0.5. Then we get two vectors, a right vector, which is a cross product with the up vector, and a down vector, which is a cross product with that vector. So this gives us kind of two basis vectors, one along the base of this plane and one along the height. And then all we do is multiply those times the width times our normalized vector. This one has to be flipped because the image is mirrored, of course. And this one, same thing with the height. And we just add that to the point, which is at the center of the plane. And this gives us a point in this plane. Then we have a ray helper draw function, which I don't really use. I only used it for debugging. Ray get world point, which gives us a point in the world, given a t. Then our draw function for the sphere, which is for drawing the spheres in open frameworks, just a preview. And then our sphere intersect function. All we do here is cast that sphere from a scene object. This is probably not best practice, but it works for now because this breaks essentially object-oriented programming, but oh well. So we intersect RaySphere, run that function, and set that t variable so that we can index by distance, of course. And we return if we intersected or not. Then our plane draw function, which is of course as well just for debugging and showing this plane on the screen, and our plane intersect function, which all it does is find an intersect ray plane. Unfortunately, didn't have time to add drawing a plane like this. As you can see, it renders all the way throughout to infinity, but that is something I have planned on fixing to the next project. So let me demo a little bit the features that the program has. So like I was showing, you can look in any angle, any direction, and you can render an image, and that's gonna render the image. It also tells you the time it takes, so about 0.4 milliseconds. Not the most efficient, but it can do. And you can see we can order the screen in any order like so, and the objects render in order. So if I go here, you can see the render takes place and the view plane updates to where we took the last render. What's another feature? Oh yeah, and of course progressive rendering, which I'm really proud of. So like I was mentioning, it takes a sampling of the scene, what it looks like, and it starts really grainy, but as the samples become closer and closer, it becomes more and more clear. And you can see this is way better for previewing what the render will look like. So just by moving and taking snapshots, right now I'm just moving the mouse and letting the screen go. And that takes kind of like the sample algorithm and shows us what the final render will look like. And it becomes clearer and clearer over time until we get the final render, like so. We can turn that on or off, and whenever we move, the image fades away. Rendering takes a little bit like so, but the improvement is if we do move, render, wait, move, render, wait. That is kind of long taking. It takes too much time, especially for a creative person or an artist who wants to render the scene continuously and see what it would look like with lighting, because that's really important if you want to move lights around and then render. So we can turn on that feature, progressive rendering, and then move around and get like a little preview of what the scene looks like without really moving. So yep, I think that's all of the features, and thank you so much for watching.